CERN's ALICE collaboration has found the first evidence for anti-hyperhelium-4, which is an antimatter hypernucleus that is a heavier version of anti-helium-4. It contains two antiprotons, an antineutron, and an anti-lambda baryon. The latter contains three antiquarks, up, down, and strange, making it an antihyperon, and is electrically neutral like a neutron. The anti-hyperhelium-4 was created by smashing lead nuclei together at the Large Hadron Collider LHC in Switzerland, and the observation has a statistical significance of 3.5 sigma. While this is below the 5 sigma level that is generally accepted as a discovery in particle physics, the observation is in line with the standard model of particle physics. The detection therefore helps constrain theories beyond the standard model that try to explain why the universe contains much more matter than antimatter. Hypernuclei are rare, short-lived atomic nuclei made up of protons, neutrons, and at least one hyperon. Hypernuclei and their antimatter counterparts can be formed within a quark gluon plasma QGP, which is created when heavy ions such as lead collide at high energies. A QGP is an extreme state of matter that also existed in the first millionth of a second following the Big Bang, just a few hundred picoseconds after being formed in collisions. Anti-hypernuclei will decay via the weak force, creating two or more distinctive decay products that can be detected. The first anti-hypernucleus to be observed was a form of anti-hyperhydrogen called antiprotons, which contains an antiproton, an antineutron, and an anti-lambda hyperon. It was discovered in 2010 by the STAR collaboration, who smashed together gold nuclei at Brookhaven National Laboratory's Relativistic Heavy Ion Collider RHIC. Then in 2024, the STAR collaboration at Brookhaven National Laboratory's Relativistic Heavy Ion Collider RHIC reported the first observations of the decay products of anti-hyperhydrogen-4, which contains one more antineutron than antihyperhydrogen. Now, ALICE physicists have delved deeper into the word of anti-hypernuclei by doing a fresh analysis of data taken at the LHC in 2018, where lead ions were collided at 5 TeV. Using a machine learning technique to analyze the decay products of the nuclei produced in these collisions, the ALICE team identified the same signature of anti-hyperhydrogen, detected by the STAR collaboration. This is the first time an antimatter hypernucleus has been detected at the LHC, but that is not all. The team also found evidence for another, slightly lighter anti-hypernucleus, called anti-hyperhelium-4. This contains two antiprotons, an antineutron, and an antihyperon. It decays almost instantly into an anti-helium-3 nucleus, an antiproton, and a charged pion. The latter is a meson comprising a quark-antiquark pair. Physicists describe production of hypernuclei in a QGP using the statistical hadronization model, SHM. For both anti-hyperhydrogen-4 and anti-hyperhelium-4, the masses and production yields measured by the ALICE team closely match the predictions of the SHM. Assuming that the particles were produced in a certain mixture of their excited and ground states, the team's result further confirms that the SHM can accurately describe the production of hypernuclei and anti-hypernuclei from a QGP. The researchers also found that equal numbers of hypernuclei and anti-hypernuclei are produced in the collisions, within experimental uncertainty. While this provides no explanation as to why there is much more matter than antimatter in the observable universe, the research allows physicists to put further constraints on theories that reach beyond the standard model of particle physics to try to explain this asymmetry. The research could also pave the way for further studies into how hyperons within hypernuclei interact with their neighboring protons and neutrons. With a deeper knowledge of these interactions, astronomers could gain new insights into the mysterious interior properties of neutron stars.